In this chapter, we're going to study kinetics, which is the study of the factors that affect the speed of a reaction and the mechanism by which a reaction proceeds. Experimentally, it is shown that there are 4 factors that influence the speed of a reaction. First is the nature of the reactants. Secondly, the temperature. Thirdly, any catalysts that might be present. And last, concentrations. So if we're talking about kinetics, we have to define what we mean by rate. Rate is how much a quantity changes in a given period of time. Like the speed you drive your car is a rate. The distance your car travels in miles in a given period of time, an hour. So the rate of your car has units of miles per hour. So the speed equals the change in distance divided by the change in time. The rate of a chemical reaction is generally measured in terms of how much the concentration of a reactant decreases in a given period of time. One can also use the rate at which a product concentration increases. For reactants, you must use a negative sign placed in front of the rate definition, because you're using up the reactants, because the reactants are being consumed in the course of the reaction. So rate equals the change in concentration divided by the change in time, and more specifically, if you're looking at product concentrations, the change in the product concentration divided by the change in time, or if you're looking at the decrease in reactant concentrations, it's minus the change of the concentration of the reactant divided by the change in time. Reaction rate changes over time. As time goes on, the rate of a reaction generally slows down because the concentration of the reactants decreases. At some time, the reaction stops, either because the reactants run out or because the system has reached equilibrium. Let's write rate equations for 2 different reactions. The first one is a fast reaction. We have A plus B reacting to form C. So starting off, the concentration of A is 8, the concentration of B is 8, and we don't have any product, compound C. In the second reaction, we have compounds X and Y reacting to form Z. And, like the first reaction, we have a concentration of 8 for X, 8 for Y, and no product, Z. So now let's have these reactions run for 16 seconds. At the end of this time, the concentration of A is 4, B is 4, and C is 4. For the second reaction, which is much slower, X is 7, and Y is 7, and Z, the product, is 1. The reaction proceeds much more slowly in this reaction. Now let's write rate equations for each one. For the first one, rate equals the change in concentration of C divided by the change in time. Now remember, delta in almost all aspects of chemistry is calculated on the basis of the final step minus the initial step. Final minus initial. So with this reaction, we're writing the rate law based on the formation of compound C, and after 16 seconds, we have a concentration of 4 for compound C, and at the initial point, of course, we didn't have any C, so it's 4 minus 0, final minus initial, and then divided by the time, the delta T is going to be 16 minus 0. We divide it out, we get 0.25. Now let's do the same calculation, but this time focusing on the rate of consumption of compound A. And the way we write it is minus the change in concentration of A divided by the change in time. And again, it's going to be final minus initial. So it'll be minus the concentration of A after the 16 seconds minus the concentration of A initially divided by the change in time. So it's going to be 4 minus 8, and of course this is going to be a negative number, final minus initial, because it's a reagent and it's being consumed. That's why that minus sign is there in the first place, to put in a correction factor for the fact that the change in concentration when you're working with reagents is going to be a negative number based on final minus initial. At any rate, you do the reaction and you come up with, again, 0.25. You come up with the same rate of the reaction as when you focused on the formation of product C. Now let's do similar calculations for the slower reaction. Let's take a look at the rate of formation of the product Z. It'll be the change in concentration of Z divided by the change in time, which is final minus initial, and that's going to be 1 minus 0. Product is 1, reagent is 0 for Z, divided by the 16 seconds. So the rate here is much slower, 0.0625. Let's work out the rate based on the reagent. We're back to putting in a negative correction factor. So it will be final minus initial. The final will be a smaller number than initial because a reagent is being consumed. It'll be 7 minus 8 divided by 16. Again, 0.0625. So here's a couple for you to try. A, B, and C is 4, 4, and 4, and at time 32, A is 2, B is 2, and C is 6. And then for a slower reaction, 7, 7, and 1, and after 32 seconds, you have 6, 6, and 2. See if you can figure out the rate for each one, the faster reaction and the slower reaction. All right, here we go. For the first one, if you're focusing on the product formation, 6 minus 4 divided by 32 minus 16, you should have gotten 0.125. Or you can do it from the reagent side, and that would be 2 minus 4 in the numerator and 32 minus 16 in the denominator, again, 0.125. Over on the slower reaction, you should have gotten 0.0625, calculating either on the basis of the product or of the reagent X. Okay, let's practice again finding the average rate for a change. Here we're going to look at A going to B, and the table here is presenting you with the number of A particles and the number of B particles rather than the concentration, but it's going to work the same. The calculation will be the same. The average rate is the change in measured concentrations in any particular time period. The average rate of reaction can be expressed as the average rate equals the change in concentration divided by the change in time. That would mean final concentration of blue minus the initial concentration of blue divided by the final time minus the initial time. And if we're going to look at the rate of disappearance of reagents, the average rate is equal to minus the change in concentration of the reagent divided by the change in time. Again, final minus initial, but that will give you a negative number because you're dealing with a reagent. So here's a question, and as I say, you can use the numbers as presented here of A and B rather than concentration. The calculation is essentially the same. Calculate the average rate of reaction for the first 30 seconds and then the last 30 seconds. And here are your possible answers. Turn your playback off, try to do it, and then come back and we'll discuss the answers. All right, here we go. The average rate from time 0 to time 30 for the blue particles would be 65 minus 0, and the time would be 30 minus 0, which would be an average rate of 2.17. And for the last 30 seconds, again focusing on the blue particles, average rate for the last 30 seconds is going to be the concentration or the numbers of particles at time 20 and time 50. So working that out, that would be 82 minus 50 divided by 50 minus 20. And that is an average rate of 1.07. Now what you should do is do the same kind of calculation, only focusing on the reagent A and the rate of disappearance of A, and see if you get the same numbers. Reaction rate and stoichiometry. In most reactions, the coefficients of the balanced equation are not all the same. For example, H2 plus I2 yields 2HI. For these reactions, the change in the number of molecules of one substance is a multiple of the change in the number of molecules of another. For example, this reaction, for every 1 mole of hydrogen used, 1 mole of iodine will also react and 2 moles of hydrogen iodide will form. And therefore, hydrogen iodide is forming twice as fast as hydrogen and iodine are reacting. If we're going to put the rate into one equation, we have to take into account that difference in stoichiometry. So we would write the rate equals minus the change in concentration of hydrogen divided by the change in time. That would also equal the change in concentration of iodine divided by the change in time. But if we wanted the hydrogen iodide rate of appearance to equal the rate of disappearance of the reagents, we have to multiply by 1/2 the change in concentration of hydrogen iodide divided by the change in time. What we've done here is taken the coefficient in front of hydrogen iodide and inverted it so that all of these terms are going to be the same number when expressing the rate. All right, so let's practice for this one. Hydrogen peroxide plus 3 moles of iodide ion plus 2 moles of hydrogen ion yields 1 mole of I3 minus plus 2H2O. See if you can write the rate equation specifying the rate in terms of each one of these reagents and products. Okay, here we go. First, for the hydrogen peroxide, we use a negative because it's a reagent. The change in concentration of hydrogen peroxide divided by the change in time. That would equal 1/3 the rate of disappearance of the iodide divided by the change in time. That would also equal 1/2 the change in concentration of hydrogen ion divided by the change in time. So that's it for our reagents, but that would also equal, in terms of products now, plus the change in concentration of I3 ion divided by the change in time, and also equal to 1/2 the change in concentration of water divided by the change in time. So let's try this one. We have N2O4 dissociating into 2 moles of NO2. Calculate the average rate for the last 10 seconds shown in this table using the reagent change first, the N2O4 rate of disappearance first, and then calculate the rate using the rate at which NO2 is formed. Turn your playback off, try it, and come back. We'll discuss it. Okay, so the rate equation is that rate equals the change in concentration of N2O4 divided by the change in time, the negative sign there because it's a reagent, and that equals 1/2 times the change in concentration of the product divided by the change in time. So let's calculate them each way. For the reagent, looking up in the last 10 seconds, that's 50 and 40. That's the time at 40 seconds and 50 seconds. We have the final concentration of 0.18 and then the concentration at 40 seconds of 0.25 divided by 10 seconds. That would be multiplied by -1 to give you a positive rate change of 0.007. If we work with the NO2, then we're going to multiply the change in formation of the NO2 by 1/2 because 2 moles of it form for every mole of N2O4 that disappears. So it'd be 1/2 times 1.64 minus 1.50 divided by 50 minus 40. Again, 0.007. The rates are equal to one another. Here's another problem based on the same data set. What is the value of X in the table at time 15? And here's a hint for you. If you want to try it without the hint, turn your playback off and try it. If you want the hint, here it comes. First, calculate the rate based on the N2O4 between time equals 0 and time equals 15. That will equal 1/2 times the rate based on NO2. So let X equal the concentration of NO2 at T equals 15. Turn your playback off, try it, and come back. All right, here it is. The rate based on the reagent is 0.59 minus 1 divided by 15, which is 0.0273. That same rate, 0.0273, equals 1/2 times the rate based on NO2. So X is the concentration of NO2 at T equals 15. 0 is the concentration at time equals 0. Divided by 15 seconds, and therefore X will equal 0.82. Answer B. Here's a graphical representation of average rate based on the equation hydrogen plus iodine yields 2HI, hydrogen iodide. The yellow line represents the hydrogen iodide, and of course the slope is steeper because it's being produced twice as fast as the hydrogen and iodine are reacting. But the problem with average rate is it keeps changing depending on your starting point and end point. As you can see, it's not a straight line. Let's do the calculations on several points. So between time equals 0 and 10 seconds, we go from a concentration of 1 for the hydrogen to 0.819. And we go from a concentration of HI from 0 to 0.362. So you know the calculation and you do it and you see that the first 10 seconds the rate is 0.0181 molarity per second. If we go a little further out in time, we calculate the average rate for the first 40 seconds. We see that for the first 40 seconds it's 0.0138 molarity per second. Or for the first 80 seconds, the average rate for the first 80 seconds is 0.0099 molarity per second. So the rate keeps changing based on your starting point and ending point. So we're going to discuss instantaneous rate now. It's the change in the concentration at any one particular point in time. It's a slope at one point of the curve. So it's determined by taking the slope of a line tangential to the curve at that particular point. And for you calculus fans out there, it's the first derivative of a function. So here's our curve of hydrogen plus iodine yielding 2 moles of hydrogen iodide. The red line represents the formation of hydrogen iodide. The green line represents the rate at which hydrogen is being consumed in the reaction. And of course the red line is a steeper curve because the hydrogen iodide is being produced twice as fast as the hydrogen is being depleted. So let's look at the 50-second point in time on the hydrogen line. We draw a line tangential to the 50-second point, and we look at rise over run. That is the value of the rise at the beginning of the line and the value of the run on the horizontal portion of the line. So we look at rise over run for this line to get the slope. We calculate it on the basis of final minus initial. So if we take the final point minus the initial point, we'll have a rise of minus 0.28 molar. And of course that's going to be corrected by a negative sign in front of that to make sure the rate is positive. And it'll be divided by 40 seconds, which is the run for this calculation of slope. So the rate will be equal to 0.007 molar per second. Now let's do the calculation on the basis of the hydrogen iodide. Again, rise over run. This time our rise is 0.56 molar and our run again is 40 seconds. But we take 1/2 of that value to make it equal to the rate at which hydrogen is being consumed. And that rate also, therefore, based on the slope of the line tangential to a point on the curve, will be the rate both for the depletion of hydrogen and for the formation of hydrogen iodide. Okay, let's try this one. For the reaction shown below here, the iodide changes from 1 molar to 0.868 molar in the first 10 seconds. Calculate the average rate in the first 10 seconds, and then calculate the change in concentration of hydrogen ion at 10 seconds. So here are the possible answers. Turn your playback off, try it, come back, and we'll discuss it. Okay, here's how we would do it. The rate equals minus 1/3, right? Because the coefficient in front of iodide is 3. So it'd be 1/3 times the change in concentration of iodide divided by the change in time. So that's equal to minus 1/3, 0.868 minus 1 divided by 10 seconds. So the rate is 4.40 times 10 to the minus 3 molar per second. Now let's calculate the change in concentration of hydrogen ion at 10 seconds. Turn your playback off, try to calculate it, come back, we'll discuss it. So the rate equals minus 1/2 the change in concentration of hydrogen ion per the change in time. So that minus 2 times the rate equals the change in concentration of hydrogen ion over the change in time. So we calculate that out, and it comes out to be minus 8.80 times 10 to the minus 3 molar per second. But the question is asking for simply the change in concentration at 10 seconds. So for this last part, we would simply multiply the minus 8.80 times 10 to the minus 3 by 10 seconds to get minus 0.088 molar, the change in concentration of hydrogen ion at 10 seconds. Okay, now we're going to look at something called the rate law. The rate law of a reaction is the mathematical relationship between the rate of the reaction and the concentration of the reactants, and homogeneous catalysts as well. The rate of a reaction may be directly proportional to the concentration of reactants raised to a power, and this power, this exponent, may be 0 if the reactant does not influence the rate. So for the reaction A plus B, where the coefficients are in lowercase and the identity of the compound in uppercase, A plus BB yields products, the rate law would have this form. Rate equals K, the rate constant, times the concentration of A to the N power, times the concentration of B to the M power. N and M are called the orders for each reactant, and K is called the rate constant. Note that the exponents N and M are not A and B from the equation. You can't look at the equation and write a rate law. You have to experimentally determine the value for N and M. Here are some sample rate laws. CH3CN forms CH3NC. The rate equals K, the rate constant, times the concentration of CH3CN. So we say it's first order in CH3CN. Here's acetaldehyde forming methane and carbon monoxide. The rate equals K times the concentration of acetaldehyde to the 3/2 power. N doesn't even have to be an integer. It just has to be experimentally appropriate. Or 2 moles of N2O5 form 4 moles of NO2 plus O2. The rate equals K times concentration of N2O5. Not squared, even though there's a 2 in front of the N2O5. Or H2 plus I2 yields 2HI. Rate equals K times concentration of H2 times the concentration of I2. Reaction order. The exponent on each reactant in the rate law is called the order with respect to that reactant. The sum of the exponents on the reactants is called the order of the reaction. The rate law for the reaction 2NO plus O2 yields 2NO2 is rate equals K times the concentration of NO squared times the concentration of O2. The reaction is second order with respect to the concentration of NO, and first order with respect to the concentration of oxygen, and third order overall. Consider this reaction. 5-bromide plus BrO3 minus plus 6 hydrogen plus yields 3 bromine plus 3 H2O. It was found experimentally to obey the rate law. Rate equals the rate constant K times the concentration of bromide times the concentration of bromate, BrO3 minus, times the concentration of hydrogen ion squared. So what are the reaction orders in each reactant and for the overall reaction? All right, here we go. So bromide is going to be first order. Bromate, BrO3 minus, is going to be first order. And the hydrogen ion is going to be second order. And overall, it's 1 plus 1 plus 2, which is a reaction order for the overall reaction of 4. At low temperatures, the reaction carbon monoxide plus nitrogen dioxide yields carbon dioxide plus nitric oxide. It's 0 order in carbon monoxide and second order in nitrogen dioxide. So the rate law is which one of these? And it's going to be answer D, second order with respect to the concentration of nitrogen dioxide. And carbon monoxide does not appear in the rate law because it's 0 order. Now we're going to learn to write a rate law from experimental data. So let's suppose we have the hypothetical reaction A plus 2B yields 2C plus 2D. And we go in the lab and we do 4 trials. In trial 1, we use an initial concentration of A of 0.125 moles per liter and an initial concentration of B of 0.2 moles per liter, and we measure the rate to be 7.25 moles per liter minutes. Then we do another trial. We triple A to 0.375 and we leave B exactly the same, 0.2 molar. And we notice that the rate also triples from 7.25 to 21.75. So now we go in the lab, we do a third trial. This time we double the concentration of A and we double the concentration of B, and we notice that the rate has doubled. For the last trial, we keep A constant at 0.375 like it was in trial 2. But we double concentration of B from 0.2 to 0.4, and we notice the rate does not change. Well, there are 2 methods to develop a rate law from these data. One is by inspection, and the second is by formula. Let's look at the inspection method first. What we must do is find 2 trials in which only one component changes and the other stays the same. So between trials 1 and 2, B is being held constant, A is tripling, and we notice that the rate triples. So right away that tells us that the rate is equal to a rate constant times the concentration of A to the first power. In other words, A doubles, the rate doubles. A triples, the rate triples. It's a first power relationship. Now what we're going to do is look for 2 trials in which A is held constant, but B changes. And between trials 2 and 4, B is 0.2, and in the 4th trial, B is 0.4, while A is being held constant. And the rate stays the same, 21.75 in each. Therefore, B does not appear in the rate law. So that's the method by inspection. The method by formula is to use this formula. Rate 2 divided by rate 1 equals concentration of whatever component you're looking at. Let's look at A again. Concentration of A in the second trial divided by the concentration of A in the first trial. So if we do that, we end up with 21.75 divided by 7.25, that's 3, and concentration of A in the second trial divided by the concentration of A in the first trial is also 3. So that tells us N is equal to 1, and therefore the rate is equal to the rate constant times the concentration of A to the first power. Okay, let's see if you can do this one. It's written a little bit differently than the previous one, but see if you can figure it out. Here's concentrations of A and B. As we go across, we get to the different trials in the vertical column. Can you figure out what the experimental rate law is? Is it A, B, C, or D? Turn your playback off, try it, and come back. We'll discuss it. Okay, so here we go. Let's compare trials 1 and 2. We are essentially doubling the concentration of A, and the rate is just about doubling. Remember, this is experimental data, so sometimes it's not picture perfect. But that's about a doubling of the rate with a doubling of component A. So that means that the rate is equal to the rate constant times the concentration of A to the first power. Now, what about another trial in which B is changed and A stays constant? Well, here we're changing B from 0.2 to 0.3. We're holding A constant, and the rate is not changing, essentially not changing. So just like the previous question, rate equals K times the concentration of A. All right, so why don't you try this problem right here? Turn your playback off, try it, and come back. We'll discuss it. Okay, so the following data is obtained for the reaction of nitric oxide with oxygen. Concentrations are in molecules per cubic centimeter. We can call it concentration. What is the rate law based on this data? So what we're going to do is take the first two trials, because nitric oxide is doubling while oxygen remains constant, and we notice that the rate quadruples. Here it's 2 and here it's 8. That's 4 times as much. So the change in concentration of nitric oxide is 2 times as much, but the rate changes by 4 times as much, and that is a square relationship. So the rate is proportional to the concentration of NO squared. Now let's try the oxygen here. And in trials 1 and 4, the nitric oxide is held constant, the oxygen doubles, and the rate doubles. So here we can see that the change in the rate is the same as the change in the concentration. Therefore, it's first order with respect to oxygen. Rate is proportional to oxygen to the first power. So, knowing this and knowing this, I would choose answer B for the rate law for this equation. Now, it turns out that the units for the rate constant K are dependent on the reaction order. And there are 3 types of reaction order that we study in this class: 0 order, first order, and second order. That is, overall order for a reaction. First, we have to assume that the units of rate equal molarity per second, but there are a number of ways that can be written. There's molarity per second, there's capital M per second, there's moles per liter seconds. If we define molarity as moles per liter, then it would be moles per liter seconds. Or we could write it capital M, S to the minus 1, meaning 1 over S. So that's the way that the units of rate can be expressed. Now, for a 0 order overall reaction, rate equals K, so K has the same units as rate, molarity per second, or moles per liter seconds. For first order, the rate, which is molarity per second, equals K times molarity. So the units of K are going to be 1 divided by seconds, or seconds minus 1. So if we have a rate constant given to us, and the units of that rate constant are S to the minus 1, or 1 over seconds, that means it's a first order overall reaction. Second order, we have rate equal the rate constant times the concentration of a substance squared. So rate, which is molarity per second, then equals K times molarity squared. And if we work that out, K in this situation is going to equal 1 over molarity times seconds, or capital M minus 1, seconds minus 1, or liters per mole seconds. So these are units of K that can tell you what the overall order of the reaction is. So now we're going to talk about a third way to discuss rate laws, and that's the integrated rate law. For a reaction A reacts to form B, we know that the rate is equal to the change in concentration of A divided by the change in time. That's the average rate. Now suppose we experimentally determine that the rate law for this reaction is going to be rate equals K times the concentration of A. First of all, what is the order of this reaction? So this is going to be a first order reaction. Remember, the order of the reaction is determined by the sum of all the exponents on the concentrations of the components of the rate law. So this is first order. Now, we can do a little calculus. No, I know you're crawling under your bed in the fetal position, but you don't have to. We're not going to get into the calculus of it. It's just that if we set the two equations equal to each other and do a little integration magic, we get this integration. Natural log of A at 0 time minus the natural log of A at time t equals K times t. And we can rearrange this to eventually get the natural log of A at time t equal minus kt plus the natural log of A at time 0. Now, does this look familiar to you? Maybe not. It's not ringing any bells, huh? How about this? Does it remind you of y equals mx plus b? Oh yes, you say. That's the equation for, ta-da, a straight line with a negative slope. So let's see how well you can relate the elements of this graph to our integrated rate equation here for a first order reaction. What I want you to do is one by one I'm going to call out an area of the graph and you can identify it as A, B, C, or D. So here we go, and just keep in mind y equals mx plus b. So for the first one, what are the units for this vertical line called the ordinate? And of course that is going to be the natural log of concentration of A at time t. Y, in other words, equals mx plus b. It's the y-axis. Okay, what's the next one? 2 is where the line crosses at time 0. So the so-called y-intercept. And that's going to be from the equation y equals mx plus b. It's going to be the natural log of A at time 0. Okay, how about the slope? What's that going to be? Y equals mx plus b, where m is the slope, so it's minus k. And finally, t is going to be the abscissa, the horizontal axis. Now suppose that instead of indicating a first order rate law, our experiments indicated that the rate law was rate equals K times the concentration of A squared. What is the order of this reaction? Well, it's second order. Do the same thing, integrate by setting the average rate equal to the rate law and integrate. When we do that, we get this integrated rate law. 1 divided by the concentration of A at time t equals kt plus 1 divided by the concentration of A at time 0. Y equals mx plus b. So go ahead and associate each part of the graph with the integrated rate law. Finally, for a zero-order reaction where the rate equals K, the integrated rate law is the concentration of A at time t equals minus kt plus the concentration of A at time 0. Again, y equals mx plus b. So If that's the case, what would this equation look like if it were graphed? A, B, C, or D? And of course, you've got a negative slope here, minus K, like in a first order integrated rate law. And when you have a negative slope, it kind of looks like D. And what would be the label for the ordinate, abscissa, and slope? And how is the term B in y equals mx plus b represented? Well, the ordinate is going to be AT, of course, because that's the y in y equals mx plus b. The slope is going to be minus k. The abscissa, or the horizontal axis, is going to be labeled with t, time t. And the term b is the y-intercept, and that is going to be the concentration of A at time 0. A zero-order reaction has a rate that is independent of the concentration of the reactant or reactants. Increasing the concentration of the reacting species will not speed up the rate of the reaction. Zero-order reactions are typically found when a material that is required for the reaction to proceed, such as a surface or a catalyst, is saturated by the reactants. The rate law is simply rate equals K. You can easily find the order of a reaction given a set of data of time versus concentration if you plot the data in Excel. You would plot it in three ways. First, concentration of A versus time. If you got a straight line with this plot, you'd have a zero-order reaction. Then you would plot the natural log of the concentration of A versus time. If you got a straight line here, you'd be talking about a first-order reaction. And if you plotted 1 divided by the concentration of A versus time, you'd be talking about a second-order reaction. So whichever plot gives you a straight line, that reveals the order of the reaction. So here's a set of data. We have time in the first column, and we have the concentration of AB in the second column. So here's what we're going to do. For the first one, we will simply make a chart using column A as our x-axis and column B as the y-axis. We select the data, we go to Insert and choose Chart, and choose XY Scatter. Well, clearly here we do not get a straight line, and that tells us we are not talking about a zero-order reaction here. So we go one more step. This time we insert a column between the time and the concentration of AB. And we choose a formula for that first cell, equals the natural log of, and then the reference cell is C1. In other words, the data in the cell adjacent to this cell. So it would be the natural log of 0.95, which would appear here. And by dragging the little dot at the end of this and dragging all the way down, you can get it to repeat this function for each one of the rows. So you will get natural log of the concentration of AB in this column and time here. Now you select both of those, A and B. Again, choose Insert, Chart, XY Scatter. Oh no, it's still not a straight line. It's not a first order reaction. All right, let's do it one more time. This time in the column between A and C, we use the formula equals 1 over C1 as our reference. In other words, the invert of 0.95. And we do that for each one of these. We select A and B again, choose XY Scatter, and now we have a straight line. So we have a second order reaction here. So one question students have is, when do we use an integrated rate law? And the answer is simple. When time is an aspect of the question, we use the integrated rate law. So, for example, for the simple decomposition, AB decomposes to A plus B, the rate is K equals concentration of AB squared, and the rate constant is 0.2 liters per mole seconds. How long will it take for AB concentration to reach 1/3 of its initial concentration of 1.5 molar. Now there are two clues here as to what type of integrated rate law equation we're going to use for this. First is the rate law is given to us, and the overall order is 2, AB squared. So that tells us it's a second order reaction. And then also we're told by the label on the rate constant, 0.2 liters per mole seconds, that's another tell that this is a second order reaction, and therefore we need the second order integrated rate law. So this is the one we have to use, the second order integrated rate law. So how do we do it? How long will it take? So we're going to solve for time t. We're given K as 0.2. The initial concentration is 1.5 molar, and 1/3 of that will be the concentration of A at time t. So do the calculation and see which one of these you come up with. Now for the reaction, the ammonium ion plus the nitrite ion yields nitrogen gas and 2 moles of liquid water. The rate law determined by experiment is rate equals K times the concentration of ammonium ion times the concentration of nitrite ion. And in one experiment, the initial nitrite ion concentration was 0.04 molar, and the initial ammonium ion was 0.2 molar, and the observed initial rate was 2.15 times 10 to the minus 6 molar per second. What is the value of K? So all you need to do is plug these values into the rate equation and solve for K. Put your playback on pause, do it, and see if you can come up with the answer. Here it is. Those of you who found that the answer was 2.69 times 10 to the minus 4, you're right. Now, what are the units of K? This is a second order reaction with ammonium ion and nitrite ion. The overall order is the second order reaction. Therefore, C is the correct answer for the units of K. The reaction of sulfuryl chloride decomposing into sulfur dioxide and chlorine has a rate constant of 2.9 times 10 to the minus 4 per second under a given set of conditions. Find the sulfuryl chloride at 865 seconds when the initial amount is 0.0225 molar. So the first thing is you have to identify which integrated rate law you're going to use. This one, or this one, or this one. And I hope you're all going to choose this one, because this is for a first order rate law. Now how do we know it's first order? The units of the rate constant tell us. It's per second, and those are units for a first order reaction. So we're going to use this integrated rate law. Now go ahead and see if you can calculate the concentration of sulfur chloride at 865 seconds. Turn your playback off, try it, and come back. We'll discuss it. All right, so here we go. The natural log of x equals minus 2.9 times 10 to the minus 4. The rate constant times 865 plus the natural log of the initial amount of sulfuryl chloride, 0.0225. So working that out, you should get 0.0175 molar for the concentration of sulfuryl chloride at 865 seconds. Now we'll discuss half-life. For a first-order reaction, you know this is the integrated rate law, and we can rearrange it to look like this. Now, by definition, when half of the reaction is complete, that is to say, when 1/2 of our starting material has reacted, the concentration of A at time t equals 1/2 the concentration of A at the starting point originally. So the natural log of 1/2 of the concentration of A at the beginning divided by the concentration of A originally equals minus kT, just plugging it into the rearranged first order rate law. So working through, minus kt equals the natural log of 1/2, or minus kt equals minus 0.693. So the half-life time equals 0.693 divided by k. Now what makes the first order half-life different from zero order and second order is that the formula does not contain a concentration of the reactant. For a zero order rate law, the half-life time equals the concentration of the starting material divided by 2 times the rate constant. And for a second order, it looks like this, 1 over k times the concentration of A0. All of these, by the way, will be given to you at the back of any exam. So for a first order reaction, the half-life is a constant. By the way, this is the same formula as is used in the disintegration of radioactive isotopes. Those are all first order processes, and you routinely talk about the half-life of this isotope or that isotope. It's the same concept exactly. The half-life for a reaction is 726 seconds. Starting with a concentration of 0.6 molar, what will be the concentration after 726 seconds if the reaction is first order? And then what will be the concentration after 1,452 seconds? Turn your playback off, think about these, and which answers would you choose for each one of these questions? All right, well, here we go. Each one of these is a half-life period. From time 0 to 726, that's one half-life period, and 1/2 of the beginning concentration would be left over after this period. So if you have 0.6, after 726 seconds, you have 0.3. If you go another 703 molar of the reagent, taking you to 0.150. The half-life for a reaction is 726 seconds. Starting with a concentration of 0.6 molar, what will be the concentration after 726 seconds if the reaction is first order? And then what will be the concentration after 1,452 seconds? Turn your playback off, think about these, and which answers would you choose for each one of these questions? All right, well, here we go. Each one of these is a half-life period. From time 0 to 726, that's one half-life period, and 1/2 of the beginning concentration would be left over after this period. So if you have 0.6, after 726 seconds, you have 0.3. If you go another 726 seconds, you'll be at 1452 seconds overall, and you would have reacted 1/2 of the 0.3 molar of the reagent, taking you to 0.150 molar. Another half-life period from 1452 to 2180 would be 1/2 of the 0.15 to 0.075. So each one of these half-life periods would consume 1/2 of the remaining reagent. So let's try this one. The half-life for a first-order reaction is 726 seconds. Now starting at 0.6 molar, how long will it take for the concentration to reach 0.1 molar? And here's a hint. Calculate K from the equation that the half-life time equals 0.693 divided by the rate constant. Solve for K, and then use that in the integrated first-order rate law. Turn your playback off, try it, and come back and check out my answer. Okay, here we go. The half-life is 0.693 divided by K. So K is equal to 0.693 divided by the half-life. Therefore, K equals 0.693 divided by 726, or 9.55 times 10 to the minus 4. That's your rate constant. Plug that into the first-order rate law. The natural log of 0.1 equals minus 0.955 times 10 to the minus 4 times the time it takes plus the natural log of 0.6. Work it out, you should have gotten 1,880 seconds. So here's our last problem. The half-life for first order reaction is 234 days, starting at 0.816 molar. How long will it take for the concentration to become 0.102 molar? And I want you to solve this without using the integrated rate law. And how can you do that? Well, look, you've got the half-life. You know what that means. And you know where you're starting and you know where you're ending. And I bet these numbers are going to be very congenial in terms of allowing you to figure it out. So turn your playback off, see if you can get it, and then come back and look at my answers. All right, here we go. First, write down the starting point, 0.816, then take half of it, you get 0.408, and take half of that, and you get 0.204, and take half of that, and you get 0.102. So for the first one, the first half-life period, that's going to be 234 days. And then for the second halving of the concentration, it's another 234 days. And finally, there's a third halving of the concentration, and it's another 234 days. So 234 days, 234 days, 234 days is 702 days altogether. So that's it for this section. We'll see you in 14B.